All right, let's see where we left off. We're going to find the area under this curve. Let's run the program. And here we have the screen waiting for us to hit a key. And that's the line segment of y equals cx squared. We're going to find the area under that. And maybe the first thing we're going to do is set up, not that we have to do it this way, but it's probably not a bad idea to use variables. And we're going to write, we're putting in the upper and lower limit. And I'm going to call a variable dx. Okay, and that's my dx. This is going to be x final. This will be x initial. Okay, and we're going to run it just to make sure that it works. Yep, same thing. And now I'm going to calculate the area simply by calculating a little area of a rectangle, y times dx, and then adding up those little areas. And this is the idea of the integration. We're integrating all the little areas. And of course, when the program is done, I want to print out that area. Let's see what we get. And for this segment, we have an area of 16.4. Well, we can compare that to what we might get using calculus. And I'll do 1/3 times c times x final cubed minus 1/3 times c times x initial cubed. Well, let's see how close we are. Well, that's pretty darn close, don't you think? Well, there's a little bit more to the story. We need to take a look and see what we're doing. It'll help us visualize what's happening. Okay, I'm going to actually draw the entire curve first. I'm going to go from 0 all the way out to x equals 8. And I'm going to visualize the curve with a larger line, a thicker line. And I'm going to use the circle command to do that. Circle just draws a circle at x comma y. And I'm going to have to specify a radius for that circle. A little thinner than that, 0.03. All right. And I'm going to remove the calculations for the area under the curve. And I'm going to put all that junk down here. I'm going to do this thing again. I'm going to set up 2 loops. And this time I'm going to be able to specify my initial, my final. And this time my dx I'm going to make a lot bigger. I'm going to go 0.5. So I'm doing this loop twice. But now instead of drawing a circle for the line, I'm going to actually draw a box to represent that area. I'm going to go line x comma 0 in the lower left-hand corner to x plus dx comma y. And to specify, I'll specify a color here, 12, and then I'm specifying a command to tell it to make it a box. And now I have to say next x. So what I'm really doing here is doing everything twice. The first time I run through this, I'm going to be drawing the line. Actually, I'm going to get rid of these. I don't need these here. I'm just going to draw the curve. And then here I'm going to be drawing the little rectangles that represent the area under that curve. And I'm going to be having a much larger dx. And we're going to get some errors here. Let's run this and see what this looks like. Now you can see that the rectangles are going to sum up our areas. And when I get to the end of the line, oh boy, there's an extra rectangle out here. Well, that's because we are going from x initial to x final. And every time we do that, we're calculating the area to the right. So I'm having one extra area here. I don't want that. And I need to get rid of that. So that means I want to stop here. I'm going to write x final minus dx. I don't need to go all the way to the end of the line. I just need to go to the point before the end of the line. Now we're going to run it. And as you can see, each rectangle adds up and it stops right there. That's exactly what I wanted to get. And then we can take a look at the error that we have. This is the second answer is the calculus answer, and the first answer is the area under the graph calculated by numerical methods. And we can see we have quite the difference. And that's true because we're missing all these little triangles. Well, we can make that better by making the dx smaller, 0.1. Now we see the answers are much better. The numerical integration is still a little bit underestimating because of those little missing triangles. And the answer is just going to get better again. As long as I make this smaller and smaller. And now you can see we're approximating the area. It's coming up nicely. And here we have almost the exact same thing. So this is a great technique if you're, like I said before, if you're trying to do the integral of a more complicated function, and we can throw in all sorts of crazy formulas in there that we wouldn't be able to do the calculus for. And that's what engineers do. They're looking for a numerical answer usually, and this will do the job. Now, alternately, the way we had it set up on the whiteboard, we used a slightly different method. We calculated what dx should be by telling the computer how many rectangles we want. Well, how do we do this? We're going to need to take x final minus x initial and divide by n. Now I know how small to make my dx. And I'm going to just count. Instead of talking about value of x, I'm just going to count how many rectangles I've got. And I'm going to go from one rectangle to n rectangles. And I won't be stepping by dx, I'm stepping by 1, and the default for that is just leaving out the step command entirely. So we're going to say x equals x initial. So I've got my initial x. We'll calculate the area the same way. And I need to specify that the x will be incremented. And I'm going to do next I. So now I'm just counting around the loop for the number of rectangles that I am going to be using in this calculation. Let's see how that looks. So we have the graph, and here come the rectangles, 1, 2, 3, 4, 5. And again, you can see a huge difference in the error. I'm going to now go to 10 rectangles. And I can go to 100 rectangles. And you can see it's getting better and better. So either way you do the math, set up the computer program, you're going to get the same results. And this is just the way we did it on the whiteboard. So maybe what you want to do now is try using this program to change the formula. Do something a little bit more challenging instead of just y equals cx squared.